Hello, we are back.
Hello, hello.
So I see a shadow moving under the table. I wonder if my feet are about to be attacked. Okay. Um, yes, so we're
So
back for the
we're at,
last session of the day. Parallel. Oh, go ahead, Simo.
yeah, I was going to say the exact same
Yeah.
thing. Yeah, you go right ahead.
Okay, last session of the day. And this is something which you need a little bit of an introduction to, but like many things, you'll probably come back to it in more depth whenever you actually need it. We're not telling you how to write code in parallel, but how if you have a code which should run in parallel, how you can actually use it and run it on the cluster.
Yeah.
Maybe,
So let's look
am I
at, maybe
going?
we should start with
Yeah.
the picture of the shared memory parallelism. Oh,
Okay, so I'm opening this page. Yes. Well, I
yes.
need to go to the right screen. There we go.
Yes.
Yes.
So yeah, we talked previously about the embarrassingly parallel and the uh like array jobs and how to run it, like lots of individual jobs basically in the cluster, and that's already like
Mhm.
very good. Like you can get a lot of stuff, but there's of course a lot more like in available left on the table when it comes to the
Mhm.
parallelism in the cluster, because the computing nodes, like these computers, they are basically the CPUs are pretty similar to what you would have in your laptop or in your computer, but there's just usually more of them. They're like server CPUs, and they usually have much more like resources. They have more memory, more CPUs. So if
Mhm.
it's possible for your code to utilize all of those resources, you can, in theory, get a lot of speed up to your code, and you
Mhm.
can get your code done faster. And that's basically this part of the parallel. So the array jobs are more like maximum throughput kind of parallel. You get maximum amount of jobs through the system and maximum amount of stuff done. And they're very good
Mhm.
if you have this kind of problem that you can split into chunks. But if you have let's say a big simulation or something, and it just takes a long time. It takes a long time, and it would benefit from having multiple CPUs to run on. Then
Yeah.
yeah, let's look how you can do that in the cluster.
Okay. Should I go to the terminal for demo?
Yeah, yeah. So when it there's two things you need to think about. So the first thing, of course, is that does your program work in parallel? Can it do stuff in parallel?
Mm,
And that's a big question. so so many
yeah.
programs can nowadays, because like many normal computers they have multiple CPUs. So they are
Mhm.
nowadays written to be able to utilize those CPUs. So for example, like if you use Python, like libraries like NumPy, scikit-learn or whatever, they allow you to use parallel uh,
Mhm.
like CPUs natively, or MATLAB does, or if you use R, you can use parallel in R to do it. And there's various ways you can run like without many
Yeah.
code changes utilized. But of
Mhm.
course, like the efficiency, whether you get best efficiency, that is up to the air. But at least
Yeah.
in principle, they could utilize multiple CPUs.
Yeah.
And to test it out in the cluster right now, maybe
Mhm.
Richard, if you run module purge to verify that there's no like previous modules loaded. Yes. So
Yeah.
we can
Confirm.
start
Okay.
by testing out an example code that we have, which is the Pi code that we mentioned
Okay.
previously in the example. So
So
we have this in the Slurm folder. There's this Pi code, and if you give it like 1,000 or whatever, like number 1,000, and if you run it like here in the login node,
mm, mhm.
okay, you see that
That's very fast.
it yes, it's very fast, but of course it's only like 1,000 tries, and this is like a very simple code, but because it only does calculations, it's quite easy to parallelize, and that's why we can use it to as an example of how do you reserve like resources with multiple CPUs.
Mhm.
So let's try running this in the queue with a bit more requirements. So if you add the normal stuff at the front there, like srun, mem,
what does this --pty mean? I
yes,
see it
so
in
we
the
didn't,
thing I'm copying.
yeah, we didn't mention it before, but you can add this --pty, and it means like pseudo terminal. So what it means that it will without the spaces, Richard.
Yeah, I'm just verifying I'm doing it right.
Yeah.
Yes.
Yeah, like the pty, it will allocate like the input and output for the terminal. So basically, if your code would have like interactive stuff and that sort of things, like it would ask for input or something, it will work. Like
it
so,
prints. Yeah. Okay.
yeah,
It makes
and it
it
will
more
print everything
transparent. It looks
automatically.
just
Yeah,
like the normal shell. Okay. Yeah.
yeah. If you're running like with this interactive srun, you might sometimes want to add the pty there.
Yeah.
But yeah,
Should
so
I
let's add a
run
bit
it?
more numbers here. So we have now is it 50 million?
It's 50
Yes.
million. Yeah.
Yes. So let's run it. It takes a bit longer. So this is about, I think, maybe 40 seconds or something, if I remember correctly.
We see srun says it's queued. And now this is doing what we learned in the interactive job part yesterday.
Yeah. And this is the kind of a program that, okay, like this could use multiple CPUs and it could run faster with multiple CPUs. So let's get first a benchmark. What often you want to do is that you want to, if you have this sort of like a program, you first want to try running it out without any bells and whistles, like with single CPU, and then see how long does it take. If you're running it already on your own computer, you can look at the process manager usually and see how many processors it's using, and then try using the same sort of requirements in Triton for that. So it shouldn't take that much more longer.
Yeah, let's see.
But we can see that like, it takes,
okay.
Yeah, okay, now we can, yeah. So it took some time. Maybe if you run quickly the SF to check how long did it take?
SF on the job ID, and it says 95% efficiency for 40 CPU seconds and 42 real-time seconds.
So if we now want to allocate, if we want to allocate more CPUs for this job, what we need to do is tell Slurm that we want to want more CPUs, and that's done with this CPUs per task flag. So we just say CPUs per task, and let's put 4 equals 4, and this would allocate 4 CPUs for that. We'll talk about tasks later. You don't have to worry about that too much right now, but that's that is the that is just a Slurm internal thing. But basically you just specify how many CPUs you want to get, and we need of course the code to understand this as well. Like the code needs to be able to utilize those, because otherwise like it might run with a single CPU. So in this case we use this nprox -nprox, and we give the same number. And it's important that the numbers match, because otherwise you might run into a situation where you reserve more CPUs than you use, or you use more CPUs than you reserve. And in both cases, like in the case where you reserve too many, you underutilize the CPUs. So you basically underutilize the resources.
Just a waste.
And if you use too many CPUs, they can get crowded. So they compete on who gets to use the CPUs, and then the code runs slower. So sometimes if you run some code in the cluster, you might encounter a situation where it runs slower. And the reason might be that it tries to use, let's say, all of the CPUs, but it's only getting one, and suddenly it's slow. So you need to tell the code to actually like use the CPUs you wanted to use. So let's try this out.
And I guess this is a hard problem. Like I've often seen codes that say it can use multiple processors, but it doesn't tell you how it actually works. So you don't know if it's doing the right thing. Is it trying to use, like, the most annoying one is when you run something and it says, oh, I'm running on a computer node that has 40 processors, so I'll try to use 40, but it's actually only been allocated 4, and it's just a huge slow down then. Okay, it's done. Should we SF
Yeah.
it?
Yes, if we check the efficiency there.
So compared
Yes.
to my other notes, this
So
says 83% efficiency compared to
yes,
95.
and we
It,
ran the same 40 seconds of CPU utilization
yeah,
because that's how long it takes to run.
I
But
guess,
now it took shorter amount of time
yeah,
in real time to
only
do that.
12 real time. Okay,
And so basically, it's nothing
good,
magical
yeah.
about like the reserving of CPUs in the submission scripts or in the command line. You can just specify the CPUs per task to Slurm, and that will give you the
Yeah,
uh,
yeah,
give you more resources. And
yeah.
there's a nice question in the notes. Are you going to answer
Yeah,
the same thing?
go ahead. I guess
It,
we're thinking the same thing.
yeah, you can say it. You can say it.
Yeah. So what I've just highlighted here, this is the argument to srun and to slurm. So the CPUs per task equals 4 is a slurm option that says, please give whatever I'm running for CPUs. And then that wraps this other command. And the nprox4 is a command that was programmed into the pi.py file, which tells it, I have 4 processors available, I can try to use them. And you can tell if these don't match up, then stuff can go wrong. Should we demonstrate what happens if you don't get it right? Or is that just, maybe people can do that
Yeah,
themselves?
yeah, I would say that it's probably good
Okay,
to.
yeah,
But yeah, so
okay,
maybe we should just jump into exercises. Like
yeah,
the exercises
okay.
basically do the same thing. So
Okay, yeah, I see it's already appearing in the
yes.
notes there.
Oh, oops, I copied the wrong one. Sorry.
Oh, okay,
Check the right one. So, but yeah, the question is like, how do you tell the program what you want it to get? Yeah, like how do you tell the program what resources it should use? And
yeah,
like in many cases, this is something like nprox. Yeah, many programs use this
yeah, it
OMP
could
num
be.
threads environment variable, and they use that, like for example, NumPy uses that to determine like how many processors it should use. There's
Yeah,
they are all listed in the documentation. So there's many like these environment variables that sometimes set these numbers. And if you look at the documentation of a library that you're using, it might say that, hey, give it the number of processors with n processors or
yeah,
n procs or n threads or whatever. Like there might be various flags for, there's no like consistent language across the board.
yeah,
So you need to look at your application and if it provides possibility of using multiple processors. And if it does,
yeah,
you need to give the information to it.
yeah.
And
There's a good question. What's the limit of the number of CPUs a program can use?
yes, that's an excellent question. And the answer is that it depends on the hardware. Like in many clusters, you have compute nodes that might have a number of CPUs might run from, let's say, 28 to 256 or something. Like it might be small or it might be very large. But like because you're all limited into this one computer, so it depends on the hardware available in your cluster. And of course, like you might reach the parallelism maximum, like at some point it doesn't run any faster after you like reach a certain number of processors. Like usually, quite often, like magical numbers might
Yeah.
be something like 8 or 16 or something,
Mm-hmm.
but there might be
I guess.
something that works with 64 or 128 as well.
Yeah, I guess it really depends on what it is you're doing.
Yeah, but
Okay,
usually it's on
so
that ballpark. So we're talking about tens to 100 processors usually.
yeah. So how long should people have to try this themselves? And is there anything else to try other than what we just did?
Let's just do this. I think that's enough, and you can run stuff in the examples and
Yeah,
run more exercises as a
yeah,
bonus exercise after the
yeah,
courses. And
yeah.
I
Okay.
will also note that in the exercise, there's a submission script that you can test out, and in that we're using an environment variable called slurm CPUs per task, which is very useful if you want the job to find out the number of CPUs like automatically. So slurm will set this number if if you ask for more than one CPU. So you can
Yeah,
use that in your code to
yeah.
determine numbers. But try it out.
Okay. How
So
much
should we
time should we
people
give people?
like 35 maybe
Till 35. So that's okay.
7 minutes or 6 minutes?
Well, 7 minutes. Okay.
Yeah.
Yeah. Okay. Then see you in a little bit.
Yeah.
Bye.
Bye.
We're back. Hello.
Hello.
So, what now? I think we'll go straight to the next parallel part and take all the questions later.
Yeah, if you want to fill out, I'm adding the poll to the exercise block. Forgot to add it previously. So if you want to fill there, if you manage to do the exercises, sorry about there being quite not that much time for these, but hopefully you got it done. But yeah, like asking the CPU shouldn't like it's basically one flag. So
Yeah.
hopefully you got it done. But
Yeah.
yeah, now we are switching gears to so this is quite a quick explanation of the overview of the MPI like parallelism, what it is. So there was already a question in the notes about okay, how can I parallelize across multiple CPUs? So how can I parallelize
Mm-hmm.
across multiple computers, basically? And this is why MPI originally was created, like the MPI thing. So MPI stands for Message Passing Interface, and it's basically like this kind of like library that allows you to do like message passing between computers and different processes running on different CPUs through various network meshes. But like people don't like when writing for these supercomputers, there's a high speed interconnect usually connecting these CPU nodes, and if you want to have like a really large program, so if you think about like I don't know, like a weather model, if you want to predict the weather, you need to have like a very big simulation of the weather happening at different places at different times, and you integrate the physics equations to get the next time step of okay, what is the weather going to be tomorrow, and for that you need like a big computer to calculate together. Like you need the whole simulation to be able to be calculated together, and for that MPI has been constructed basically, and it's still a standard in many of the supercomputers when it comes to this kind of big scale programs. And so what is important to remember about MPI is that it's either or. Either your code uses MPI or it doesn't. So if your code doesn't, if it hasn't been constructed around MPI, if it hasn't been constructed in a way that like it will use message passing interface, it won't use it. So
Okay.
like
Yeah.
it's very important to remember that, like, if it uses MPI, if you see in the documentation that there's an MPI build of this, or you can add MPI support or whatever, then it uses MPI. Or if you build a program from the ground up to use MPI, then it uses MPI. But if it doesn't, then it doesn't. And
And
there
I
are
guess
other
making a
methods
new
of
MPI program is a very big process. So
yeah, depending on the program. But yes, usually it you need to like figure out whether your program can use MPI. But there's already like lots of programs, like especially physics programs and that sort of stuff that use MPI on the background.
Okay.
And for those users of those programs, this is a very good way. Like you just install your program with the MPI capabilities available, and then you can utilize multiple computers at the same time.
Yeah. So should we do the example?
Yes. Let's look at the example. So we have the
Okay.
Pi version written with MPI like support, and because like you need to bake it into the program, so the Python version doesn't cut it. Like there is this MPI for Python that you can use to use Python and MPI together, like, which is a nice library if you want to start, if you just want to use Python, but that requires additional libraries. So for this example, we are going to use a C, like C compiled, like C version of a program that does the exact same calculation that the Python one did, but it does it in C and it uses MPI.
Okay.
And
so how do I start?
So in order to, usually when you have an MPI program, the first thing you need to do is you need to load up the MPI installed by the cluster administrators, because the MPI is tied directly to the queue system, and it's tied to the network infrastructure. So it's very laborious usually to install the MPI. So that's why the system administrators usually provide it, and you install your code using that MPI. So
this will be different for every cluster. So
yes.
Read
so
the docs.
If you run module spider MPI, open MPI is one flavor of MPI. That might be something you want to use.
Okay.
So then we can compile our program using MPI CC. So if you type MPI CC -o pi -mpi and then slurm pi mpi.c.
Okay.
Yeah. So what this does is
okay.
What it does is it compiles this pi.mpi executable that is now like MPI capable. You can check the like what the source code is if you want to. But now, okay, like we have this. Maybe you should try running it with srun with the normal stuff and see how it goes. Like if we just put like 10 minutes and 500 megabytes of memory and just run it. So without anything, it should run similarly.
How many steps should I do?
Let's put the same 50 million. It shouldn't take that long because it's C code, so it's faster than the Python code.
Let's see. I bet it will be very fast.
Yeah. So it's quite a bit faster. So
should we SF it?
Yeah, sure. Yeah.
So it said it used 1 second of CPU and took 1 second.
Yeah. So it's quite a bit faster than the Python version. So that's how it usually goes if you use the lower level stuff instead of like higher level languages. Of course, Python can be fast if you use the correct libraries, but
I mean, that's why you write a C library and run it from Python.
Or you use NumPy, and that's fast itself. But in this case, let's try now adding some more MPI tasks. So you notice that in the output it said that like what was the computer's name where it was running, and then it says something about rank. So MPI has these MPI ranks. So basically, it's just every CPU in the or every MPI tasks gets this rank number. So it's similar to the array ID, but in this case, they are like a collective. So in the MPI, everybody works as a collective, and they get this number. So we can ask for more of these tasks. So previously, when we saw the CPUs per task kind of a situation, so these are now the tasks that we are requesting. So if you give to the srun n tasks, nodes 1 and n tasks, let's go with 4, yeah.
Yeah, okay.
And let's add at least 1 0 at the end, so we get some like reasonable,
something.
like 10 times, make it 10 times harder, so maybe it runs for a few seconds. So
okay.
So in this case, what we are asking the queue system, we are asking, okay, give me one computer and give me on one computer, give me 4 of these MPI tasks. So we didn't mention the CPUs per task here. We are asking like these MPI tasks. And what it does basically that when the program starts, it starts the individual programs, and then each of these like connects into a collective that then solves the problem together. But if you use the n tasks without an MPI program, you run into all sorts of problems, and the same program might run multiple times and overlap. So don't use the n tasks if you don't have an MPI program.
Okay. Yeah, and I guess the PyMPI, we didn't tell it how many tasks there were, so it sort of automatically knows what's available.
Yes. It creates this communication world where everybody knows about each other, and then they can do the work together. And you might see here that the output is a bit scrambled because everybody works independently, and they might print out stuff in different orders. Like some might print out stuff before the other tasks. So
it's like 1 starting, 0 it's done, and then 2 and 3 report they're starting. So, but that's pretty typical when you're trying to do this stuff.
Yeah.
Anyway, should we SF it?
Yes, let's do that.
It used 9 seconds of CPU.
And the efficiency wasn't
3 seconds.
Yeah, because the efficiency wasn't that good because it's still so short. So if we would have increased the
like these numbers are so short, it's not good statistics. So it's clearly taking this times 4 and dividing 9 by that. So but okay.
And in the notes we have a good question of like, does it mean that the n tasks 4 that we run 4 independent tasks, and they are not independent, they are a collective. Like in MPI, everything is a collective, so there's like four tasks running in the same collective, which is the whole program. So like, let's say you would run with 30 computers, like 30, like if you run in Mahti, or if you run in Lumi or somewhere like a really big machine, you might run with, let's say, 1,000 processors. And in those cases, you need to run with, let's say, 20 computers. So you might ask for 1,000 tasks and then like get that from the queue system.
And technically it's not threads here, but it's independent processes that communicate between each other. But if that doesn't make any sense to you, it really doesn't matter.
Yeah.
So
but yes, so this MPI is still like, for many like bigger things, it's still very like very heavily utilized. But it's like, for many of the smaller programs, it's usually better to use the array structure in addition with the shared memory parallelism to run your stuff, because this requires like your program to support this from the ground up, basically.
Okay, so what now? We've got 12 minutes left. should we give people time to try it themselves and then come for
Yes,
a wrap up? Okay.
I will copy the commands we run. In here also there's the SBatch script that you can use to run this in the queue. And do note that if you're running this in this queue with the script, you will want to add the add the srun before you run the program. And the reason, well, it depends on the cluster, but in most clusters you want to do this. And the reason for that is that the srun basically ties the program to the queue system that then tells the each program like that they're part of the collective. If you don't run it with the srun, they don't necessarily understand that they're supposed to know about the other ones. Because everybody, like basically Slurm starts like multiple processes at the same time, and all of those call home and ask like, who am I? And then they start working as a collective. So if you don't add the srun, then the program doesn't necessarily work as intended.
Yeah. Okay, there's the exercise stuff. So should we return at what time?
5 maybe
minutes?
Again 5 minutes and then have a wrap up.
Yeah. Okay. Well, take a short bit of time, see what you can do. See you in 5 minutes, and bye for now. Hello. We're back. All 4 of us. So,
Yeah.
What's the wrap up here? From the notes, there's some good questions. Question like, what does nodes and what does tasks mean? The different MPI implementations. This can get really deep really fast, and I guess we're not even trying to go into it that deep.
Yeah.
So
I highly suggest looking at our documentation and other sites' documentation if you plan on using any of these frameworks. Like the problem with, I would say, like there was a great feedback that there should be more exercises, and I completely agree. But especially for these topics, it's very hard to have exercises because they depend so heavily on the application. But the main thing to remember, I would say, is to remember that these are the paradigms like that are usable in the systems. Like if you have a program that mentions something about like something about threads or workers or whatever, it usually means that you can use multiple CPUs. And if you have something that mentions MPI, then it usually can use MPI. And like remembering these words and these connections allows you to then ask the queue to provide you those resources. But those exact flags you want to use and exact implementations you want to use differ based on the cluster. And then it's good to look at the documentation. But basically, like in order to make the connection that, okay, now we're talking about this sort of approach is very good, because then you can like make certain that your code uses all the resources it can use.
Yeah. And I see in the notes here, there's 2 questions about weird internal MPI errors, which are caused by who knows what. And yeah, this is what I think of when I think of MPI. So, having to figure out the cluster thing, get your code working, get all the problems solved. It can make stuff run faster, but it takes some time to figure it out. And at least if you're at Aalto, come ask us rather than digging into it, unless you just want to dig into it, in which case, by all means, go ahead. And I don't think we can really answer these here. Who knows what it is? I guess you've probably seen there's feedback of the day here. You can start filling that in. Is there anything about parallel or any other general questions we should answer before we leave for the day? I guess if so, write them down any other general questions we may have missed from before, or you'd like us to talk more. So what's the expectations for day 3 now? But we covered what was in the schedule. Are there many exercises and hands-on things tomorrow? Does anyone know?
Well, at least
Looks like
in the GPU part, we will be doing some small examples, but again,
yeah.
it's bit of a depends on the application you're using. So it's
Yeah.
it's
Yeah.
quite a hard thing to say. And in the LLM session, in the example, we will definitely
Mhm.
like show you how you can do stuff, at least here in Aalto, and we show
Yeah.
code that you can use to run local LLMs. But yeah, it's we will have hands-on exercises, but of
Okay.
course,
Good.
yeah, depends on how involved you want to access the.
And we also have 2 philosophical sessions. One about how to ask for help with supercomputers, which is a talk written by one of our collaborators in Norway, but I'll be presenting. It sort of gives you some insight for, when and how and what it's like to ask for support. And then there's a wrap-up session at the end of the day, which has 20 minutes budgeted. And what's usually happened other years, sort of all the instructors come here and you can ask us all the questions about anything at all. So all of the big broad things, putting stuff together, and we can see what happens there. So yeah, so do stay for that. And I guess there's nothing special to prepare. If you have access to the cluster, you can probably run the stuff we do tomorrow. The GPU stuff may be different on different clusters, so it would be good to review the GPU info for whatever cluster you have, and then come prepared with that tomorrow to see if you can get it working. Or even see
and
if you can get it working over
and
the night.
if you're hungry for more exercises, like all of the tutorial pages linked in the material, they have at the end multiple exercises. If you want to do them and give, even better, if you want to give feedback on if you had done them, like how could they be improved, or which one would you want to see in the course, let us know. That would be great.
Yeah,
But no worries, like
yeah,
there's no homework, there's no like, we don't force you to do something if you don't want to do it. But if you feel like you still have the hunger to write some Slurm scripts, do go and check the tutorial pages.
yeah. Okay, great. Should we wrap up for now? And I guess see you
Yeah.
tomorrow at the same time.
Yeah.
Come prepared for all your stuff. Yeah. Okay. Great.
Yep.
Have a good, or wait, was there any other feedback questions? No questions.
Lots of love for the cat.
Yeah. Thanks for all the stuff. Hopefully Kat will come back tomorrow. It's only morning, so it might be sleeping. Okay, great. See you later.
See you.
Bye.
Bye.